Hello, Aaron. How are you?
Hey, Dmitri. Pretty good. How about you?
Doing good, doing good. Thank you. So it looks like arrows on the clock start to roll quicker than usual for all of us.
Mm-hmm.
I was hoping that we all live an easy life without urgent activities, but I'm not sure it is possible. Hello, hello, Eric.
Hey, how are you?
Doing good, doing good. Thank you. How about you?
Okay, I want to understand this system. Just a second. Shoot, gosh dang
So let me make you both as
it.
we need to present something. Okay. And maybe I can slowly start and show something from the paper you did show and from the result that Aaron computed, and then it will be like little pieces, and then you show the bigger picture.
Okay, sure.
Okay. So it will be not the whole big picture, just little pieces, but maybe we can enjoy and develop something out of it. Okay, here. This is the preprint you did share, and there is a big. I'm looking very narrow, not on the big picture, but on the narrow thing. There is a challenge that we experienced in previous work, and it tracks us here. So there is a manganese overlapping with conduction band, and there is not much manganese seen in the valence band on the available for optics. So
Okay.
and if the models like this are, I would try to be brave and say they're not applicable to describe experiments because of good or wrong reasons. So it is qualitatively wrong picture. And now I will show some good news. So here are slides that Aaron prepared cooperatively with some input from Salim and maybe Talgat. So the model here is substantially smaller than realistic one, but just skipping details. Here is the emission spectrum as function of energy in electron volts, and there are transitions here, which we call like from exciton, and there are explicit transitions that DD transitions from manganese. So they are qualitatively at the right place. They both coexist in this model. And if we look on the electronic structure, there is no p-bills, but it's not a big problem to do. The frontier orbitals here and there are contributed by d orbitals on manganese, which is qualitatively correct. So this model has substantially, it's like a small cluster. One would need to justify why we do so terrible approximations in modeling. But since it gives right energetic and correct qualitative picture, maybe we can invest and consider it further. So I think this results of primarily Aaron plus Salim plus probably Talgat are substantial help to interpret. Now I'm stopping. I want to stop sharing and sorry for using precious time. Now steering wheel is in your hands.
Who, me or Aaron?
Maybe you can start with global overview, and then Aaron
Yeah.
will do whatever.
Well, this is all single exciton stuff.
Mhm.
Addressing your email, okay?
Mhm.
And I think, I don't know, I can't share my screen with, can I share my screen with you guys?
I believe so. I
Yeah,
made,
yeah, okay. So here, hold on then. I don't have a little pen like you, right? So first of all, I just have a couple questions. What is the Bohr exciton radius for these materials without the dopant?
I wouldn't say from the top of the head. Aaron, do you?
It's fairly small, like I guess the radius people say like 2 to
Okay,
3 nanometers.
so then here's a question. Can you see in my screen in this PDF
Mhm.
right here?
Yep.
So if you look for no manganese, right?
Mhm.
This is exciton PL versus size. Why does it keep going up? This looks like confinement to me, but these are well above the Bohr radius of the material, right? So we should be out of the confinement regime, at least in a simple view. So Ken, how would you explain that? You see my question?
Yes. I do not have explanation, but I can just make fantasy and dreams. So if we consider the nanocrystal chopped on little boxes with confinement in each of them, then it will be applicable. But what forms the borders between these boxes? I don't know. Maybe if manganese ions are homogeneously spread, then little areas between manganese or opposite little area around each manganese can be, I don't know.
This is the trend with no manganese at all, though. So this is just pure cesium lead chloride, right? Excitonic emission. The gap gets smaller as you get bigger.
But if we forget about formation of exciton and consider that it will be particle in the box independent of bound electron hole states. By the way, there is a big dielectric constant, and probably exciton binding energy is not as big, right here. So it is heavily screened by epsilon around 1000. But if you forget about excitonic effects and just look for like particle in the box, what is the typical change of energy if we modify the size between like 5 and 7 nanometers? Would it be this small 10 nanometers, or it will be bigger? I don't know.
Well, yeah, it goes from about 400 to 410. So
I would expect from particle in the box confinement, it should be a little bigger than that. We can focus on ourselves or ask Aaron to help to get actual figures. So I like the idea to see connection analogy with confinement, but should confinement give more drastic change in the transition energy?
you mean this is too small? I see your point.
And on another, if we are speaking about excitons in perovskites, in two-dimensional perovskites, yes, excitons are famous and strong, but in bulk and nanocrystals, I have little reservations and doubts because of the dielectric constant. So,
well, remember our previous paper, right? Here, let me pull that up. Hold on a second here, just a second. This guy right here.
Oh, so the best paper from Fargo.
Most recent, I think, yeah. But the point being that if you look, granted, this was bromine, right? Not chlorine, but here you can see it right here. So
So changing in the range of in this range of it is much bigger.
it should be steep, right?
Yes, yes, it is not like 10 nanometers. It is like I don't know, 50 or 100. Let's
So what is the exciton, Bohr exciton radius for bromine, cesium lead bromine? It must be bigger, right? Is that right, Aaron?
Yeah, it's bigger because like it has a lower dielectric constant. I think the numbers I usually see thrown around is like 5 nanometer.
Well, this isn't too far off that. I mean, it looks like right at about 6 is where you get above 8 and you're definitely starting to flatline, right?
Yeah, and those numbers, I think those are just straight from effective mass, so they're fairly like crude for perovskites because it doesn't include like the additional dielectric.
So let's just do a quick calculation here. Going from 6 to 4, you're talking about going from 2.5 to 2.7. Okay. You're talking about a big shift, right? That's your point, right, Dmitri?
Yes.
Yeah. So back to here, then that would seem to suggest that this really isn't confinement, right?
Or some it is not. Yeah, it is. If it is analogous to confinement, it's some I don't know, light version of confinement.
So what could be causing it? That's what I'm wondering. It's a puzzle to me. So let's see, 400 to 410. I mean, that's like it's insignificant, 100 electron volts, right? It's a very small change from the view of confinement, but nonetheless, the trend is very clear. And it's the same with, start adding dopant. Doesn't really change till you get to, quite a bit of it. I'm just trying to, how do we understand the undoped limit? That's all. So usually when we see this thing, a curve like this, where you go up in size and the system redshifts, we immediately think, aha, confinement, right? Like we did with silicon. Remember that? But this is such a small shift. It must be something else. See, if we can't understand that, that's going to be hard to understand the dopant, right? Because it's the simplest system is the system without the manganese, right? So, yeah, I gotta understand that, because I was up until now under the impression that this was the usual confinement, but I don't think it is. The length scale isn't right, right? And the shift is too small, unless, well, let me just think about it. 5 to 7 nanometers. It'd be like, second here, 6. That'd be. Is the Bohr radius for chlorine smaller than bromine? It is. Okay. So that would suggest that in the case of chlorine, this curve should shift this way. So maybe it is confinement, but it's just you're on this really, really weak
screen confinement.
It's got to be screen, yeah, L -2, right? So, a safe bet would be that chlorine is the same, but it's just shifted to lower length scales. but you still have a size dependence here, right? So it's possible. So for example, let's just do this. What do we have here? We go from 400 to 410, right?
Mhm.
And this was at 5 nanometers, and this was at 7 nanometers, right? So this would be 5 nanometers, 7 nanometers. You're talking about going 5 to 7, you have a very small change. Yeah, that probably is what it is. It is confinement, but it's just kind of on the weak tail of it.
Mhm.
Does that make sense? Does that seem
Yep,
correct?
yeah, it's good working hypothesis. I do not
Is that,
see.
is that something good to have right now? Because then everything makes sense, right? Because
Mhm.
yeah, we just have really nice data. Because we can resolve that, high size tail of the confinement regime. And then you start adding the defects, I'm sorry, the dopants, it doesn't change, right? Until you get past this threshold where you really have quite a few of them. Right? Does that seem good?
Mhm, mhm.
Okay, so here's what I think's good. So now, first of all, yeah, this paper I showed you. Do you know these guys at Harvard? Do you know this guy, Sasha?
Mhm.
No?
Mhm.
See, I think the problem with this paper was the experimental part, not specifically. You look at his absorption data. It's not good. Where is it? Here, right? But what I think is right is this idea that the absorption cross-section is a strong function of dopant. So for example, Aaron, you spun a few different parents, right? Do
Mhm.
you think that the concentration of the parent at the top of the gradient was always kind of the same? Or could it vary?
You mean the excess?
No, so you take a little load of parent, you put it on top of the gradient right before you spin it, right?
Right,
You take that from a parent solution.
right.
Was the concentration of that parent solution, was that more or less the same every time you did a spin, or did it vary with parent?
Um, I mean, there's some variation, but it was like the more concentrated, like the material I put in, the better the spin usually turned out.
Okay. Do you think it could vary by as much as a factor of 2? Because what I did was I looked at the absorption measurements of the fractions, comparable fraction number, so comparable size, as a function of the doping content of the parent. And what I saw was that the absorption tended to go up as the amount of dopant went up, which is consistent with this right here. Okay. So the reason I bring this up is because if you go to our paper, okay, and you come down here, okay, all right, you can see right here, right at this critical size, you get kind of a bump in the radiative rate and a bump in the non-radiative rate. My thinking is, and at this size scale, you have about 15 dopants per nanocrystal, right? So I think what you're doing by adding the dopant here, by increasing the size at fixed dopant concentration, is you're just increasing the likelihood that you're going to make an exciton. Because if the exciton, like these guys seem to claim, and maybe you guys can comment on this claim, right? If the exciton is localized around the dopant, which is the whole gist of their argument, all right? And what you're doing is by adding more dopants, is you're creating more friendly sites to create an exciton, even though you're still only making 1 per nanocrystal, right? The cross section for that has increased, right? So in that picture, what's going on then is that you have, you get to some optimal number, but then once you start adding more dopants, they start to interact. And that interaction is what causes it to start going downhill again. So you can see this here, even when you don't have strong dopant emission, this is pretty low dopant concentration. and then it becomes enhanced at higher dopant concentration. You see? All right? So that's kind of where I'm leading to now, is that there's two separate things going on. You have the dopant acts as a passivating agent, which is why the quantum yield, why the non-radiative rate drops out here and the quantum yield goes up, right? Because here you got dropping non-radiative rate, flat radiative rate, and here you've also got increasing quantum yield. See that? All right. Now for the other one, right, they're both moving together. So you've got, you know, the radiative rate goes through some kind of a peak, right? And then it starts to go down. So here, this is where the quantum yield is a maximum. So what's different here? You've got more dopants, right? So now this length scale, where this happens, is a little bit smaller. You see, 5.6 nanometers as opposed to 6 nanometers, okay? But the only reason this has anything to do with localization is just because you can pack these sites in and make the whole thing more efficient, up to a point. Once there's too many, right, then they start to feel each other, right? And then the interaction of the dopant takes you into this new regime, right, which is where this non-radiative guy starts to really climb and the quantum yield starts to drop. Does that make sense?
I do not see objections, but it's still digesting. Let me share a crazy thought which may be irrelevant. Just so if we have no dopants, there is a network, and we are considering only conduction band. We do have network of LEDs, and there is a like hopping probability. So there is a one electron wave function is spread by being delocalized of several LEDs from each edge. If you completely replace each LED by manganese, then there will be similar network of manganese, and conduction band wave function will be also like spread over all manganese. And then if you replace all LED with manganese, it will also obey some sort of confinement, and it will lose some properties if you further increase it. So those are two limiting cases. And if we like look into this eutectic, or how to say, mixture of the lead and manganese at the sites, there could be the effect that you did mention, that manganese helps constructively when on the side of the curve when it is ascending. And then when there will be too many of those, their interaction makes a network of manganese to feel the edges and obey confinement in some way.
Yeah, that part makes sense, because that's what you're seeing. Oh, wait, I gotta, hold on. That's what you're seeing here, right?
Mm-hmm.
Because now you've partitioned the nanocrystal into smaller nanocrystals. So, you know, accepting the caveat that this is all just weak, a signature of weak confinement effects, right? Then suddenly you partition you got enough dopant that you partition it into smaller sizes. That's kind of the working hypothesis we had for this, right, Aaron?
Mm-hmm.
Yeah. So associated with that is a redshift in the dopant emission, right? So what does that mean? Would that has to tell us something as well, right? Because pretty much everything is right around 600 till you get to this 2, which is kind of the, you know, the highest dopant level we considered, right?
So
And then it shifts.
Just for understanding, 1.5, 2.0, it is concentration of dopants.
It's
right?
the feed, yeah, the feed ratio.
So basically, you are looking you fix concentration and then scan the size of the dot. So there will be a range of dots which differ by size, but ratio of manganese to lead is constant.
Right, so what's changing with size is the number of manganese in there, right? And again, you can see there's this critical size. Right here, it's about 5.8, right? And then you see that again. This is the one that goes with it. 5.6, right? Somewhere like that. It's like you go through this, you go through a transition. You see that? This is the quantum yield. It goes up and up and up, and then all of a sudden it starts to go down, right? And what's going on in the region where it goes down, right? This corresponds to this region here, right? Where this guy levels out and then this guy jumps and starts to climb. So then the question becomes here, how does adding more dopant cause a redshift? How, or do dopant interactions, how do they shift this red emission?
Without detailed analysis and study, I will answer in the spirit of the previous crazy idea. So you're telling increasing concentration of dopants induces redshift.
Yeah, it makes a redshift in the dopant emission, and it causes a drop in the dopant quantum yield. So there must be something going on, and you can see that actually in the non-radiative. It's a really nice set of data that we got. I just don't understand it yet. Here you go, see this? So this is the non-radiative. What's beautiful is that right where the dopant emission is most efficient, the radiative rate comes up and the non-radiative rate comes down, right? And then this guy takes off, right? So this guy takes off. That means all of a sudden, because of these dopant interactions, you've got all kinds of non-radiative channels, right?
Right. I sense, I feel the smell that there is an effect. So if concentration is low of dopants, then as in considerations of like impurities, I don't know, in like NV centers in diamond, impurity looks like almost like an atom in the vacuum, isolated. It doesn't have resonance states to transfer energy or whatever. If we increase concentration, then it will be a band of these impurities, and they have transitions between each other that will add additional non-radiative transitions. So we should consider either like a band of slightly degenerate states of impurities, or I can offer this like crazy idea of vacuum, if we forget about lead, filled with high amount of manganese ions, and there will be a wave function spread over all manganese, same as particle in the box. Or again, as a limiting case, I do not tell that we need to do the following numerical experiment, but we can consider a model where all leads are replaced by manganese, and I put a bet that the gap energy will be substantially lower.
Yeah, that seems to be the trend it's going in. If you look at this data again, right here. Again, these are relatively small shifts, right? But you can see it's getting redder and redder and redder as you get bigger and bigger. That has to be some kind of dopant interaction effect. Right?
I would again, it needs more thinking, but I would put, if it would be a presentation on a like big audience, I would put nearby the figure from textbook showing the formation of bands, where one level, two level, and then multiple levels converting to continuous band. So if you go to higher concentration of manganese,
so then the band edge becomes lower and lower, and basically.
Yes, because here is one, here is several. Energy levels always repel each other, and then the lowest one in the band will be lower than the isolated one.
Okay.
And the mechanism of repulsion, it's additional story, but
Yeah.
it happens. It happens. No matter any interaction, just splits energy straight.
Okay. So then, really, so the other thing that's interesting is, so like, okay, so this figure here, right? This goes with this top set right here,
Uh-huh.
and this figure here goes with this bottom set, right? Okay. Both of these show this effect, this dip in lifetime, this peak in radiative rate, right? Okay. Well, what's interesting, and where I believe this paper now is wrong, okay, is that if you come here and look in this range, right, by this argument, you would expect the quantum yield to go up, but it doesn't, okay? Region 2 here, quantum yield is flat, right here. In fact, it goes down a little bit.
Mhm.
You see? Okay. So that's where I had to get confused, because he keeps talking about oscillator strength. I mean, they tie everything back to, I'm just trying to figure out how much of this paper is right and how much of it is wrong, so I know what I can use to think and what I should ignore, right? And you said that you don't think this paper's right?
Well, there are objective challenges, objective difficulties with DFT application to this transition metal doped semiconductors,
Okay.
and we faced this challenge with Aaron. So paper went through, but still we understand that it is there are some things that must be better. And one of the potential reasons that DFT is single configuration, maybe there are some additional tweaks with functionals, but it is quite clear expectations that this manganese doped things must be occupied and unoccupied inside the band, inside the forbidden band, inside the band gap. And here, in this last panel, the conduction, the unoccupied manganese overlaps with host matrix. Yeah, this yellow. And the invalence band, I think there is a little sub peak, but it is not on the frontier in the valence lower in the occupied. We either do not see it, or it is completely overlaps with host matrix, while it should be similar yellow peak above the valence band.
I see.
So it creates qualitative confuse. And when in the paper with Aaron a couple of years ago, we were considering photoluminescence of manganese doped perovskite. It was really low, like orders of magnitude lower than one would expect in reality. And it is primarily, my understanding is due to the qualitatively wrong alignment of levels.
Okay.
So the only thing by today we can do is to manipulate the concentrations. Like if we go to a limit of very small clusters or confinement shifts homos and lumos to higher energy on one hand, and very high concentration of manganese and also specific functionals, then we can get correct alignment of levels. But it will be hard to defend because atomistic model is a little bit different to what is on the experiment. So it is like,
I see the challenge. Yeah. I think what we should do is I should think about your simulations and you should think about the experiments. I don't know how much attention to pay to this paper then. Like I said, I don't, you know, there's the thing that I think is most interesting about our paper is this whole
yes,
size dependence.
I agree.
And the fact that, you know, you have something, you know, you're not changing much, you're not getting much bigger here, but you got a lot going on. And there's like a critical point, right? So the only thing that I can see that defines that critical point is the distance between dopants. I think that's the critical thing, right? So, and obviously you won't be able to simulate that, right? Because
Let me suggest. I'm not sure if I will be able to do myself or to offer to anyone else, but maybe Aaron, if you have empty slots in your schedule, what if we try to take Salim's model and replace each lead with manganese? So if there is a correlation between modeling and experiment, by replacing each lead with manganese, the gap should decrease, and radiative processes should be not as good as in the like low concentration. So let me share screen and briefly show what I would expect. So if one takes a model with manganese only, and I'm trying to reproduce this figure with only manganese. So this peak will appear more redshifted. Its intensity will be smaller compared to what was here. Yes, that's it. And then it will be trends that one does see in experiment. So with no manganese, it will be like higher energy. With some manganese, it will be maximal oscillator strength and at certain energy, and with all manganese, it will be even further redshifted, but intensity will be lower.
Yeah, that might be a good way. How hard would that be to do?
It's for this kind of small model, it is again, we all are busy, and I think Aaron is busier than we are, because he's trying to go for early defense. But it could be, with all stars in the good arrangement, it can be done in like a couple of weeks.
Couple of weeks?
Yes. Quicker, it is not possible. With even if you put all efforts and work as a team.
Oh, I don't think, I mean, a couple of weeks is fine. I don't understand this well enough yet to start writing, but this would give us a good way to link the simulations to the experiments. Now, this is dopant states, right? Right here? Oh, sorry. The DD, what you call DD in your little drawing, that peak in the density of states?
Yes.
That is the dopant, correct?
Yes, it is D2D. It is manganese related transition.
And these other ones up here above it, those are exciton, right?
So this one is exciton, and those could be some hybrids. I better ask Aaron.
Yeah, I'm not sure. They're just transient, so it's just, I'm not exactly sure where they come from, but they're very short lifetimes. So they just occur during the cooling.
Okay.
But the main, yeah, but the peak that has 10 to the third counts, those are from the dopants.
And then, and the one at the highest energy is the exciton?
Yes.
The one Dmitri has in red?
Mm-hmm.
So
if you
I
look,
guess what I'd be interested to see is how those peaks evolve under the circumstances what Dmitri said, like no dopant, little dopant, you know, optimal dopant, and then way too much dopant.
right, and I guess to help, the figure to the right of it is the computed absorption spectra.
Mm-hmm.
So the dopant doesn't absorb at all, so there's no features there.
That's what you'd expect, yeah.
Mm-hmm. And then the first kind of exciton absorption peak is this little red one.
Okay, yeah.
And so yeah, that's.
And then can you do this dynamics? Okay, the blue plot where you got the two rate constants, one for an electron, one for a hole, right? You see that? The one middle top. You can do that kind of a dynamic experiment for each So this is all just at one dopant concentration, right?
Yes.
Is that right?
Hmm.
How hard would it be to do it at, say, 3 or 4, including no dopant at all?
There is no technical challenge. All codes are debugged and running, but the non-adiabatic couplings needs to be computed along MD trajectory, which takes time.
Okay,
There is the specifics of this code that it parallelism is limited to some extent, and to get trajectory and couplings, even for small systems, it takes time.
that would seem to me to be the best way to try to connect to the experiments. Because really, if you go back, here, let me show you my,
Yeah, let me stop showing. Oh,
yeah, I got it.
Mhm.
Share screen. Right. Okay. You know, we're well above the confinement scale, right? So all of this you can view as coming from just changing the amount of dopant molecules, right? And you'll never be able to simulate these because they're too big, right?
correct.
So what you
Correct.
have to do is try to find an analogous situation that you can simulate, and that would be
Your words are honey to my ears and to the heart. If
well,
you
you
can
gotta
say
be
so, it's
you gotta be realistic, right?
yes, yes.
What I'm saying is that's kind of what I'm looking at then in what you just showed me. You know, if you can, obviously you're not going to change size. You're going to keep size fixed, right? And then you're going to change dopant,
Mhm.
right? Okay, but that's just, you know, you got two axes here. You got size and you got dopant concentration, right? And really what we have is we're looking at a two-dimensional space, right? In that plane of dopant numbers and size, right? Okay.
Mhm.
And we have in our data, we have really good size resolution at a couple different dopant concentrations, right? But one thing we could do with the simulations is just fix the size at something that's reasonable and accessible and meaningful, right? A cluster, like you say, and then change the dopant numbers.
Yes,
I
and
think that's the best way to try to get insight.
excellent.
You-
And
you
it looks
agree?
similar to what we did with 2016 with Sam Brown and John Fogel, when there were temperature dependence of silicon luminescence.
Mm-hmm.
Most important figure for comparison of theory and experiment. It was two trends in logarithmic scale,
Yeah,
and they were very off in absolute values, but on logarithmic scale they were parallel to show the same dependence.
exactly. So what I'd be looking for, go back to your screen then,
Mhm.
okay?
Yep, just a second.
Yeah, so two things, you know, how does this guy change from no dopants to a lot of dopants?
Mhm.
And then how does this guy change from no dopants to a lot of dopants?
Mhm.
That, if you can do that, we should be able to find enough common ground to get some insight. See
Okay.
what I'm saying?
Yep.
What do you think, Aaron? Is that feasible?
Yeah, that's the models are small enough that like it's easy to work through everything on a reasonable time scale.
I mean,
And
it's not apples to apples, it's apples to oranges, but you know, we would be looking for qualitative changes, not necessarily quantitative. Because we've all played this game enough times now, right, to know what the limitations are.
mhm,
Does that make sense?
it does, it does. And if it would be purely computational paper, then reviewers could bite us for doing incompatible size. But if we explicitly tell that we need trends and we understand the risks, then it will be really great thing. Of course, if you find what we see, if you have this
Well,
trend.
so I'd be curious in these excitonic rates, these rate constants. So what do they do
Mhm.
as you increase the number of dopants per molecule, right?
Mhm.
No, I don't expect that we would be able to, I'm going to cut you off again and do mine. I'm not expecting that we'll be able to reproduce these trends exactly, but what I would be looking for would be some kind of change in rate constant associated with the exciton. And then for the dopant, you can't do dynamics, right?
We do dynamics with dopant. It's fine.
You can.
Yes. With this oversimplified small model, we do.
Okay, could you show me that on your screen?
So this is doped model, and if we look, so this excitation is what we call exciton. Those region here are transition states that give this small peaks. And then most of the time system resides on the HOMO-LUMO, which are manganese, both occupied and unoccupied are manganese 2+ localized states.
I see.
There are rates, how quickly it goes from one to another. So Aaron gives here numbers. And also, it is not shown here, but one can also get the radiative and non-radiative rates for recombination, which contribute to this height of this peak.
The oscillator strength?
Oscillator strength for radiative and rate of recombination for non-radiative.
I see.
This is computed through the dynamics. So it is already in the procedure. We are not reinventing anything. We just apply, so to say, existing instruments to slightly new system.
Well, I think that's what we should do then. And then we should look for insight there. I kind of feel like I have a pretty reasonable understanding. I mean, I don't quite understand, right? I don't quite understand yet, the full, what's causing this peak, right? Obviously it's dopant numbers. But maybe we can get some insight there, because what you'd expect to see then is some kind of, some kind of flipping. So this is non-radiative rate. This is non-radiative rate. Let's just keep chewing on. I'll keep chewing on the experiments while you're working on those simulations. Does that sound reasonable, Aaron?
Mm-hmm.
So what's the time?
Yeah, definitely.
How long do you think it'll take you?
I mean, the part that would have the most like creativity is just figuring out what the correct structure is, because if this dopants are interacting, they can have multiple like spin alignments, so they can be ferroelectric, ferromagnetic, or anti-ferromagnetic. So I have to spend some time sifting through which electronic structure is the lowest. But then once that's figured out, everything else is kind of just machinery.
Okay. All right, and then I'll keep chewing on this in the background. But before you guys go, I know you got a group meeting coming up. I just want to ask one more time. You got my screen still, right?
Yes.
I want to know again, this paper. Should I ignore it? This is not a fruitful way of thinking, that you're localizing the exciton, and by localizing the exciton, you're increasing, because it doesn't seem to hold, what they're arguing here doesn't seem to apply to our system, right? Because we see an increase, right here, for example, an increase in radiative rates, but there is no increase in quantum yield. You see? So if you read that paper, that's what Klimov saw. So this guy goes to great lengths to explain why he sees something that Klimov didn't see, right? And I think the reason is because he doesn't have good resolution. He doesn't, if you look at our parent data, they hide, right? So you go back to our figures, okay? Go back to the parents, okay? You see some suggestions of this, right? But nowhere at the level of detail that you see when you do it in a size resolved fashion, right? So that's the part that I still don't quite understand, that I'm still working on. But according to you, I should ignore this paper in terms of the simulation end? Don't believe any of it?
Well, I mean, from my takeaway from it, it's kind of like it's like their explanation is kind of like a graduate level project description. Because basically what they're saying is if you take away a lead, which has 6s orbitals, so it's further away from the ions, and
Yeah.
you replace the lead with the manganese,
Mm-hmm.
it's like they have 4s orbitals. So it's kind of a given that like 4s is more localized than 6s.
Okay. Do you have any handle on the size of the, or where the exciton is in your clusters with respect to the dopant? You
I mean,
understand
it should be delocalized. So the excitonic wave function has two components: the envelope, so from the
Mhm.
boundaries,
that? Yeah,
and the atomic centered sites. So I guess what they're saying in that paper is that the atomic centered sites, there's more
dominate.
localization to those, but the
Yeah.
envelope function shouldn't really change because the boundaries don't change.
So, because what I have to understand that I don't quite understand yet is why there's sort of a critical point, a size dependent critical point, right? So you're at 6 nanometers, and then here at 5.6 nanometers, right? You increasing size here, you're basically increasing the number of dopants, right? Because it's not a huge jump in size, but there's obviously a lot happening. So the only thing that can explain that is you have some critical number of dopants, and I'm just trying to understand this number 15 that you got. All right, so here, right around here, you got 15 dopants for nanocrystal, right? That gives you a length scale. You divide up the nanocrystal into 15 subvolumes, right? I still don't understand that part. What's going on? And maybe it is some kind of confinement effect. I'm not sure. I have to think about that. It doesn't seem like it should be, but well, maybe it is because of this guy right here.
So I apologize. We need to meet.
Yeah. Okay. Thanks.
Let's probably plan on either wait until Aaron is done, or we can meet. Make another intermediate meetings during the
I
break.
think let's just wait till Aaron gets done. You see what to do now, Aaron?
Mm-hmm.
Okay.
Yeah,
So,
just
and while you're waiting, I'm going to keep thinking about it. If I have a question, I'll send you guys an email. How's that? Does that
Yep.
work?
Oh,
Okay.
sure.
Thanks, guys.
Yeah, many thanks. It's quite inspirational, inspiring work.
We got
I'm sorry that I need to disconnect. Just people will be waiting.
Yeah, gotcha. Okay. See you guys. Bye-bye. Yeah.
see you.
See you in the other room soon.
See you in a minute.